Hello everyone, and welcome to our fifth Tismat webinar. I am Agata Papotto and I'm project manager at EBN, the European Business and Innovation Center Network, and I've been supporting the organization of the Tismat webinar series with different services providers who are presenting different validated characterization techniques and user cases. Today, we have the pleasure to have Georgia Kastrinaki from the Center for Research and Technology, Hellas, CERT, and she will present a session on the Raman Spectroscopy, available tools for battery research. Georgia will be leading the main session of the webinar, and if you have any questions or comments during her presentation, please feel free to share them in the chat box, and we will have a Q&A session right before the end of the webinar. Just before we get started, I would like to give the floor to the Tismat project coordinator, Fabien Perdu, who will give us some background information about the Tismat project. Fabien.
Thank you, Agata. So I will not take long, but I will just introduce the Tismat project, which is an open innovation test bed for electrochemical energy storage materials, and why we are introducing this new test bed. So the context is that the European battery market is growing very fast at around 25% per year, which is enormous. And we have to develop in Europe a competitive battery value chain. It's one of the top priorities of the Commission. And for this, it is necessary to progress in electrochemical storage performance. And this progress depends on characterization and understanding of all the basic processes which happen inside a battery. There are some advanced techniques which are developed in our research labs in Europe, but they are usually underused by the companies. So, Georgia, please.
Oh, sorry.
Thanks.
Just say next, okay.
So, the Tismat aims to provide an easier access to these advanced characterization techniques for the domain of electrochemical storage materials. It's in three, let's say, successive objectives. First is to set up the platform to provide this access to the characterization and modeling and so on. And second is to demonstrate that this platform has an added value. And to demonstrate this, we solve some user cases. And the third one, which is now taking place, is to make sure that this platform will grow and will be financially sustainable even after the end of the H2020 project. So next, please, Georgia. Yes, in the consortium, we have mainly two types of partners. Some of them are service providers, such as CEA or CERT or ESRF and so on. And they provide some characterization techniques on various aspects of the material, chemistry, morphology, structure, performance, modeling also. And the other half, let's say, of partners is the service users. It's typically industrial companies which have problems with their materials or their cells or their components, and which come with a user case with questions. And so this user case will find answers in the techniques provided by Tismat. In the middle, we have Therma, which is the single entry point and which dispatches the needs of the service users to the right techniques of the service providers. And CEA is coordinator, but CEA has also a second role, which is taking care of the database, where all the samples, tests, and results of the project are stored and structured. And of course, there is a strict access control to ensure that only the people supposed to have access to this data can really access it. Next picture, please. Just to give you an overview of the timeline, in fact, we should update this slide because today is rather near the end. The project has had a third phase of setting up the organization and a second phase of testing the platform. We are in this second phase where Thermatech has taken the role of single entry point, and where we are also looking and involving new partners as external service users, which are like future customers, and external service providers who could become also future members of the consortium after the end of the project. Because after the end of the project, we will enter a phase of commercial activity. So there is no more European funding, and the Tismat platform will be autonomous and will live from its customers. And I think it was the last one.
Yeah.
So
okay.
Georgia.
Okay, thank you very much, Fabian. So good afternoon from me as well. So today we will talk about Raman spectroscopy. I will just give you the basic principles of the technique so you can get a good introduction on what we are trying to study. And then I will show you some examples. First, let's say an easy to handle example, which is a study of cathode active material development, what we can see with Raman spectroscopy, and then we can go to some more complex analysis that we performed on battery materials that we received from our industrial partners during the Teesmat project. And at the end, I will show you the principles of operando Raman spectroscopy. Now, what is Raman spectroscopy? In order to have a Raman spectrum, we need to have a laser source and matter, typically any kind of matter. So Raman spectroscopy is a method of non-elastic light scattering when matter, gas, liquid, or solid, and the solid can be amorphous or crystalline, is illuminated by monochromatic radiation. And the scatter radiation that we receive contains the new spectroscopic region. So I will explain you in later what this ray light and the Raman scattering are. So the first observation was by Sir Chandrasekhara Raman, who observed this phenomenon in 1929 and received the Nobel Prize in Physics in 1930 for his work on the scattering of light and for the discovery of the effect named after him. Now, the basic principles are quite simple. So you have a laser source and you beam a molecule of a sample. So this absorbs the energy of the laser and starts to vibrate. So you have a vibrating molecule. So when the molecule stops to vibrate, so it gets back into its initial state, we have emission of, and it's we have a scattering of the light, and it's the ray light scattering and the Raman. So in principle, what we do is we have a filter between our detector and the vibrating molecule to cut off this the ray light scattering and just collect the Raman. Now, just to go into a little bit into the energy levels of this vibrating molecule. So we have the initial energy, which is in a specific frequency, and once the molecule absorbs it and then emits it back, we have the ray light scattering, which is exactly in the same energy as the initial one, and then we have two kinds of inelastic scatterings, which is the Raman. Now the Raman is comes in two kinds of modes. So the one is called the Stokes and the one is the anti-Stokes. So you can hear these are very simple virtual energy levels. So in the ray light, we have during the excitation a certain energy level, and then during emission back into the initial energy level. In the Stokes, we have excitation into a certain virtual energy level and then emission back into a higher one than the initial one. And the anti-Stokes is again excitation to a higher one, and then during emission we get into the beginning, into the initial one. So since we have this, which is actually the wave number of the laser, we have the Stokes in higher wave numbers, and then we have the antistocks in the lower wave numbers. Now, in terms of a frequency, for 10 million counts of raylight vibration, we have 1 of Raman. So we need quite strong laser sources to detect such a phenomenon. And as we said before, we have a filter that is actually cutting off these very intense frequencies and just allowing the Raman to be detected. So this is a typical spectrum, for example, of ethanol, and this is the wave numbers that we showed before. So literally, when we're talking about Raman scattering, we're talking about the shift that it has, these wave numbers have to the raylight, and this is the part of the spectrum that we are always studying. So when we're talking about Raman spectroscopy, we're talking about the Raman shift of our modes to the laser source. Now, which molecules are Raman active? As we said in the beginning, we can have gas, solid, or liquid molecules, but actually not all are Raman active. We need to have certain molecular symmetries in order to those molecules to be Raman active. So typically, very known symmetries are that of ammonia molecule and water. So in ammonia, we have the C/3, which is we need to turn in the molecule into a 360 via 3, so 120 degrees, in order to get exactly the same molecule. And the same is with water molecules when we turn them to 180. So here are the basic elements of symmetry that we can meet in when we're studying molecules. So we have the rotation axis, it's this n-fold that we just explained. We have the plane, which is the kind of mirror that we have in our molecule, the center, where we have the center of symmetry, and rotation reflection axis, which is quite the most complicated, and then you have to turn vice versa your molecule in order to have the same one. Anyway, we'll not go into these details. Just to show you some examples also of what we're talking about. So this is the symmetric stretching vibration. It's actually the most common vibration that we will meet in Raman spectroscopy. Most of the molecules that we study are according to this symmetry. Also, we have asymmetric stretching, and also we can have scissoring, and we can have many others. But I'll just show you these examples. Now, this is a micro-Raman instrument. This specific one is from Renish, so it's a very known industry of producing Raman systems. It's a very compact one, and it's one of the 3 systems we have in CERF. It's very easy to use. It's basically for engineers who are doing applied science, so you don't have to be a very physicist, let's say, to know very deep inside the Raman in order to use this. Is very applied. So what happens into this system, but it's all automated. When you use it, you have a laser source, and by different mirrors, you just follow your beam into the sample. You focus onto your sample, and you define what part of the surface you want to study. So literally, you have just seen the microstructure, let's say, of your sample by a lens, and then you focus the beam, and then by backscattering, you just follow the Raman part into a holographic edge filter where you open up your beam, and then you have this is led to the spectrograph and the computer and to the detector, and the computer gives you this Raman spectra ready to use it. Now, this is what's inside when we open the hood. So we have an automated stage. This is fully automated, so we can perform 2D and 3D analysis of our samples. And we have different kinds of lenses in order to study to have different analysis of our samples. And literally, this is how we load a simple material that we want to study. This is a cathode that we put that under our lens, and we are ready to study. Now, an example from energy storage applications. So we tried to develop an active cathode material, literally from a non-cobalt active material. It was from the LNMO family. It follows a spinel structure, and we try to dope it with iron, magnesium, and aluminum in order to see different kind of effects in its capacity and different aging and cycling. So literally, this is the structure that this spinel follows. So through calcination, we can manage to have the disordered phase, which is this FD3M. And here you can see the different lithium, manganese, and nickel ions into how they are formed into the lattice structure. And this is a typical spectrum of the LNMO of this disorder structure. So we will focus on this, specifically on this peak here, which is on 630. And it's attributed to the symmetrical stretching vibration of magnesium and oxygen in this magnesium oxide octahedral sites. So here you can see the different kind of laser spectra that we got for the different kind of materials, where we actually try to substitute nickel in our structure through iron, aluminum, and magnesium. And you can see that we have a shifting into lower wave numbers of this specific bond. And this can be related actually to the bond distance of this molecular bond. So what happens is that the iron exhibited the higher wave number shifting. So this means that while trying to substitute nickel here in this lattice, we had a shrinkage, let's say, of this molecule. And what we saw is that what happens is that it turned out to have a better stability of our material during high cycling and high voltage cycling. Now the rest of the examples are from the Tismat project, as Fabienne explained to you at the beginning. We have a project that is actually what it's trying to do is that it can help the European industry for the time being, and we hope international industries in the coming future, to give us problems that they have, and we try to develop during the project different kinds of techniques and test them in order to give them solutions and try to optimize their materials and their processes. So the first example that I will show you is from UNESCO, who is a partner into the project. UNESCO is a known company for supercapacitors, and but they're also developing lithium-ion batteries. So what they wanted to do is that they wanted to study the fresh and the end of life, the cycled cathodes and anodes of their batteries, to see what happens into their the composition, the chemical composition, or what may be the degradation effects. And the cathode that they provided us was LMO, which also follows the cubic structure that we saw in the previous example, and also LTO, which was the anode, which also crystallizes in the FT3M space group, which is the disordered. Now we studied these materials ex situ, which means that we received fresh and also cycled they which were dismantled. They were coin cells that were dismantled by CA. They were washed out with different solvents. So we received cathode and anode electrodes, and we measured them under the Raman with a single point spectra. And also we performed Raman mapping, which is some chemical images that are created by the different the peaks related to different peaks of the Raman spectrum. We'll explain you in a while. So this is what we see literally under the microscope. So we can understand immediately if we have some kind of inhomogeneity, which was not the case. Both of our samples seem quite homogeneous, so there's nothing different to see, let's say. But if we go back, if we go to the chemical composition, first of all, we need to analyze our spectrum so we can understand exactly what are the types of bonds that we are trying to study and we're expecting. So this is the spectra that we get from the LMO. So we can divide it into two major categories. So at the high wave numbers, we have the active carbon part, and at the beginning of the spectrum, we have the LMO part. And what we saw when we compared the spectra of the fresh and the aged cathodes was that we had a shifting of this main peak that is attributed to LMO. We'll show you in a while exactly what we are talking about. So something very typical that we do in a Raman spectrum is that, according to the literature and to the theory, we're expecting different kind of vibrations according to the structure. So, for example, in the LMO, here you can see exactly what are the type of vibrations that we are expecting. So it's more than one. And but the most prominent one is that one. So it's 5, which is the manganese oxide. It's also the vibration that I showed you in the previous example. So this is the vibration that has the major shifting. And the other one that we also see to have quite a difference was this one, which is related to the dilithiation process. So it's also manganese, but manganese in this kind of structure. And once we see a shifting in this mode, we understand that it's the lithiums have been extracted. So here are images of the Raman mapping that we can create. So at this point, what we say to the software is that we want to have, in terms of colors, we say that we want to have the shifting of the peak. So we say that the blue ones are more attributed to the fresh sample, which is the 610. And those having lighter colors, the green and the red, are attributed to 640, which are more let's say the aged, where we expect the aged formation. And what we see here, that this is the fresh sample. So we see that more of the sample, of course, is having this blue color in our image, and the aged cathode exhibits more the red color. So we immediately understand that during aging, we have a shifting of our peak with the manganese oxide. Now this is exactly what we see here. So at the fresh one, we have more peaks are here, and while we cycle the material, we see that the peaks go more to the 620, which is related to aging. Now the second map here is attributed to the peak of the specific vibration mode. So the more intense a peak is, this means that the better the structure. It's not like XRD when we have crystallinity, but it's like it has a very the bond is quite strong, let's say. But after the aging, we see that the intensity of this peak also falls down to lower numbers. So we can see that the structure is more or less, we can't say degraded, but it's kind of degraded. So it's not as strong as in the beginning. And here at the last slide, here we can see the peaking. It's the ratio of the the bond, the F2G, with the vibration, which is related to this dilithiation process. So we can see here that after cycling, more parts of our material have strongly been dilithiated. So we can understand the mechanisms of degradation by our chemical composition. Now, the second material that we observed was the anode, the LTO. So again, we had no differences in terms of morphology, let's say. So both materials are quite homogeneous. And again, we have the spectra of LTO. Again, we divide it in two regions. So this is related to active carbon and this is to LTO. And these are the results that we obtained from the fresh and the cycled materials. So what we see again is that we have small shiftings in basically in these two vibration modes, and this is the EG, and the A1G again. This is related to the spindle structure of LTO, and these are the mappings that we obtain. So again, we have it's not like we have a decrease of the intensity if we compare the fresh and the cycled spectra, but what we see is that we have a higher concentration of the regions having the LTO. So we can also see that part of the 610. So we have larger areas of having red. So it's not that homogeneously, it's not that homogeneous anymore. So we have alterations of our chemical structure. And the second example I will show you is that the one on the Genesync. So Genesync is a company that is doing copper ink printing, and they're doing electronics, but they're also printing copper foils on organics or on organic substrates. So typically they had an issue with in changing of the color of their material. So probably it was caused by oxidation. So they wanted to study this effect. So they sent us fresh samples that we left them to age for some months in ambient conditions. And we saw that the color indeed was changing. So we wanted to see what type of oxidation it gets. So we again performed the situ study, which is a study of the material as it is. According to literature, we have three types of copper oxidation states. So we have the copper 4, copper 3, and copper 4. Copper 2. So the lower the copper strength, this means the most oxidized. So this is the highest oxidation state of copper. So from morphology, we can see that we can have different kind of colors, and here we can have some dark spots and also some white lines. And if we go higher to resolution, we can see exactly how it looks like. And we tried to compare the different kind of spectra obtained from different kind of regions. So here you can see that we have, this is probably a problematic region that needed a further study. So we have here a source of oxidation, and this causes different kind of color as we move away from the source. So we took spectra from the different spots. So from, let's say, a non-problematic region, and at this point, and then at this point, which is closer to the circle, and finally at the source. And you can we compare them here. So you can see that this is let's say less oxidation, the lower oxidation state of copper. And as we move on further to the spot, we see that this is decreasing. So it's higher for the fresh state. And then we have the copper 4 actually, which also has the same tendency. But as we move forward to the spot 4, which is this the source probably of oxidation, we see that it's copper oxide, so it's totally oxidized. So we can see that for some reason they have some spots of, which is some spot of oxidations, which we cannot understand how this happens, but this later, let's say, it's transferred to the whole structure. Now, finally, and last, I will talk to you about the operando Raman Spectroscopy, which is a tool that we are CERT is currently developing, and we hope to have it in the asset of Tismat at the end of the project. And this is an operando optical measurement electrochemical cell. So which means that we actually inside here are synthesizing electrochemical cells that we later observe them by our macroscope or our Raman laser. First of all, this cell it's very compact, so it's quite small. So we put it inside the glove box, and we can load it with different kinds of materials that we want to keep them under controlled environment. So, for example, our aged cathodes or our different kinds of materials that go under oxidation or are very sensitive to humidity are studied inside such cells. So we can understand exactly what's the chemical composition and not after different kind of reactions with the environment. And typically this is how we synthesize inside this cell, for example, a lithium ion cell. So we have our counter electrode at the bottom, so we cannot have optical access to this if it's according to this structure. Then we put on the separator. Then on top we put a mesh. It can be copper or aluminum. It depends on what's the electrode on top, if it's a cathode or an anode. And then we put on our working electrode, which is deposited on again on copper or aluminum foil. And at the top we seal it with a glass window, and we have different kind of windows depending on the kind of measurement we want to take, and also if we have to know that this material will not react with the electrolyte. And once we seal it, there is an open, we can open here, there is an open hole that we can put in the sealing our electrolyte. Now, if we see a section of this cell here, it's quite different from the typical, for example, lithium-ion batteries that we know, because here we have, for example, for a half-coin cell, we have our lithium metal here on top. We have a separator, and then what the lithium sees is actually the copper foil, and on top we have our active material, which can be observed by our the tool that we have on top. So at the beginning, when I wanted to synthesize the first cell, it was quite challenging because literally I did not understand. Usually we have the electrodes, the one facing the other. So in a typical electrode, actually, you have the surface of the anode and the surface of the cathode, and then you have a separator in the middle, and then you have the intercalation of the lithium ions inside the anode and vice versa again to the cathode, but the cycling. But at this point, you have something quite different. So what happens is that actually the lithium ions do not follow this route, but the working electrode is actually receiving the lithium ions from the side. So it's a different kind of inspection. So you actually have them during, if this is, it's a graphite strip. So during intercalation, when you are charging, you have the lithium ions coming from the outer part to the inner part, and then during discharging they move up back again from the outer part. So what I found interesting is that this is all from the EL cell company that we bought this electrochemical cell. So you can actually have different kind of operation modes. So one of them is that actually that you can have them the one beside the other, and you put the separator on top. And they have a very interesting video that I wanted to show you so we can understand exactly what are how this thing is working. So here you can see the graphite part here. So what you see is what you see from the top, from the microscope. So here you have the graphite part, and at the other part you have the lithium part, the lithium metal, and they perform different kind of cycling. So you have different modes of charging and discharging. So I will show you this video. So we can start with the charging. So you can see the lithium ions. Actually, it has it's been charged with a very, very slow rate. So you can have a charging, then discharging, then you have this formation of the lithium dendrites here, and then again it charges, begins to charge again. So we have, you can see the changing of the color due to intercalation. And then again, we have discharging again, formation of the lithium ion, of the lithium dendrites. And then we have cycling again. So actually you can understand that we can have we can observe the chemical composition. So once we have the laser beam on top, we can understand the changes in the chemical composition by the different spectra that we get. And just to sum up some of the advantages of the Raman spectroscopy technique with the state-of-the-art equipment that we have. So it's a technique that is non-destructive actually. So it's non-destructive as long as, of course, we keep the laser in a state where it's not oxidizing our material. So we need to study this, but it's a non-destructive technique. So we don't need sample preparation. In terms, it's not. It can be exposed to air. So we can have a molecular bond characterization. So we can see the change of the molecular bond and then we can compare and have to see the change of the structure. We can have point-by-point characterization, and by that we can perform also surface characterization, and also we can perform volume characterization of the material under specific circumstances. It's being characterized by the short measuring time, so we can have under 1 second one spectrum, and we can also have a high resolution of our material, so we can measure down to 0.5 micron, and we can also adapt the environment that we want to study our material, because we can have cells with optical window, as I showed you. So for battery studies, we can study the cathode, the anode, the electrolyte, the separator, and the binder without further treatment. We can study the chemical composition and changes of the chemical composition, so we can see what kind of reactions are taking place on the electrodes. So by this means, we can study the SAE and the solid electrolyte interface and the cathode electrolyte interface. We can study the fresh and the cycled materials. We can understand the interface of the different components by performing 2D mapping, so we can see how the active material is related to the conductive material, to active carbon, and also what effect has the binder. And in terms of morphology of the solid electrolyte interface, we can have surface characterization, and also under certain circumstances, we can also have volume characterization of it. And finally, we can perform in situ electrochemical cell testing, which can also lead to very interesting results considering the chemical, how our materials are under cycling. So at this point, I would like to thank you for your attention.
Thank you, Georgia, for your presentation. I guess we can now leave the floor to some questions. So if some of you have any questions you would like to ask, Georgia will be happy to answer them. Feel free to unmute yourself and ask questions if you wish.
Yeah, if there is no, then I will ask one question. So thanks, Georgia, it was very, very interesting. For the operando part, so you show result from the microscope, I would say. After, I mean, from the data of Raman, how, I mean, electrolyte is affecting, or at least could you see electrolyte with the Raman?
It depends on the electrolyte, but what's the, let's say, the advantage of Raman spectroscopy is that you can directly focus on the part that you want to see. So if your beam is not, let's say, focused on, if it's focused on the cathode, you can get information on the cathode. But if it's, let's say, somewhere in between, yes, you will receive also spectra from the electrolyte as well.
Okay, so then it means that you can, I mean, if you are putting it, let's say, at the interface between the electrode and the electrolyte, you could possibly, I mean, probe what happened at the interface.
Yes, but yes, that's what we are trying to do, actually. It's, but you need to focus exactly on the interface, because if you are, let's say, focusing somewhere else, you will probably get a signal from there. So yes, if you focus on the interface, you understand what's happening on the interface.
Yeah. Okay, great. Yeah. Thanks a lot.
You're welcome.
Any other questions?
Yes, I have a question. Sebastian from CA. I don't understand, how do you manage to obtain images of, for instance, the dendrites growing? So it means that you manage to have a laser in a cell being working electrically. So how do you manage to do it? I don't understand.
You mean about the last one, the operando testing, or on the previous slides on the operando?
I think it was the last one.
Okay. So you're talking, for example, on this kind of structures, not on the results I showed before.
Yes.
Okay. So what you see here is what we also see on the microscope. So literally, this can be the electrode of a working cell. So what happens is that here it's the lens that the beam comes out. So we immediately target and see it under the microscope, the part of the electrode that we want to study. And while we have the cell cycling, we get the spectrum from this specific point, let's say. So did you, I hope it was understandable how this kind of cell is working. So it's not like the two electrodes are facing the one the other. It's just that the lithium ions are getting from the side.
Okay.
So it's the same kind of operation. No, it's the same chemical reactions happening, but it's a different kind of operation.
Okay, thank you. It's clear.
Okay. Yes, Didier, please. Unmute yourself.
So Didier from ESRF. Yeah, here on your picture, I have actually a question. It's because you're not using a grid, right, for the copper foil current.
In this one, actually, there is, but it's not put for for better looking. But you have to, actually, you need to have a grid here somewhere, which is a mesh. It's a mesh, which means that the electrolyte can also come in and out, and also that actually the electrons are led by this mesh to the system, so we get the current at the end somewhere. So this mesh is somewhere. It ends up somewhere in the system, and the electrons go to the potentiostat.
So have you performed some in situ measurements with such a configuration?
Yes.
Yes. Don't you have any trouble with the swelling of the active material with the beam focus?
Yeah, it's one of our yes, it is one of our issues. So actually during high beam activity, because what we do is that we're trying to optimize the technique right now. But what happens is that indeed by beaming, the electrolyte gets increases its temperature, and it's one of the issues that we have. But what we have seen is that by using a higher wave number in the laser, so we have 532, but now we're trying with 758, we see that the increase of the temperature is much lower. Mm-hmm. So this is one of the things we have tried to optimize the technique, let's say.
Yeah. You can also reduce the range you scan.
Yeah.
To limit the exposure time, right?
Yes, correct.
Yeah. Thank you.
You're welcome.
Okay. I don't see any other questions in the chat or not other raised hands. Unless anyone has something to add, I guess we can close this session. And I would like to thank once again Georgia and Sert for organizing this very interesting webinar. Thank you very much.
Thank you very much.
Thank you. Repeat it, please. More webinars like this, please.
Thank you.